Welcome to Brain Vision.
Okay, in this problem we have a cathode ray tube being operated at 18 kilovolts and 60 milliamps X-rays. We're given some additional information about this target. We're going to assume that it has a mass of 0.25 kilograms, and we know its specific heat is 130 joules per kilogram Kelvin. So we're first asked to find the power of this cathode ray tube, or how much energy is actually per second is going into these X-rays. We know that only 1% of the tube's energy is going into these X-rays per second, but we need to find what that power actually is. We also, and this is the slightly more complicated question to be asked and answered, we need to find the rate change of temperature for this target if it's being supplied with this energy and it has these material properties M and C. So the equations we're going to use, the first one should be familiar to you. It's the power, which we can get on IV. In an electrical device, we know we can put the plug power in for 1%, 0.01. The energy being multiplied per second would be the current times the voltage, IV, P equals IV. And we have to include this little efficiency factor, epsilon, to account for the fact that only a small amount of that electrical power is actually going into the X-rays. Now, D, capital T, temperature, change in temperature over change in time, we can arrive at this expression. Power, we need to find something, we need to have an expression that has seconds. So we can, using some dimensional analysis, we can construct this expression. So we can say that P so doing a little bit of moving around, we have joules up top divided by grams, joules, we're left with, this is what we're going to need to get the second part, plus electrons in this particular power. So finding the power being delivered to gamma rays is relatively straightforward. And V of 18 kilovolts, so 18 e to the 3. And we end up with 10.8 joules per second, also known as a watt. So that's a really simple result for the first part. Now to get this rate change in temperature, T dot, or dt over dt, we can use the expression that I motivated earlier, the power over MC, plug in our results, 10.8 joules per second, divided by the mass of this target, 0.25 kilograms. It's pretty small target. And C, the specific heat, which is 130 joules per kilogram degrees Kelvin. So after plugging this all in, and I'll just do a little confirmation. Yes, we are left with 0.33 degrees Kelvin per second. So this target will actually, according to the calculations, will get hot relatively quickly. It's rising by 1/3 of a degree every second. That's a little concerning. So in this very last part of this problem, these are the main numerical results that we were asked to find. At the end of the problem, it's a little bit of more of an exploratory exercise. They ask for which materials would be most beneficial for a design of a cathode ray tube for the target. We can see, because the amount of temperature increase, it depends on the power over MC. Assuming that we want to minimize the amount of the temperature increase in this target, which I think is valid, we don't want it to get extremely hot, we would need to increase M and C as much as possible. So we would ideally be looking to minimize heat transfer to the target, we would want to increase M and increase C as much as possible. So we want to max M and max specific heat. So we could take a look at a table with showing lists of specific heats and lists of mass per unit volume. One that jumped out to me that has a very high specific heat is concrete, which in addition to being pretty massive and having a very high specific heat is also pretty relatively inexpensive. It doesn't have to be this very exotic material. So perhaps this would be an interesting material to use. Anyway, there are plenty of other materials that you could consider by looking at a table of specific heats and masses. We were asked to find the rate change of temperature increase. We found that, 0.33 Kelvin per second, degrees Kelvin. And we were asked to find the actual power delivered to X-rays, which is 10.8 joules per second. So that's it.